Okay, what I'm going to do with this video is, first of all, take you briefly through gravitational potential energy and work done by gravity. The reason being because you should have some familiarity with this. In the next videos, what I'll do is I'll take you through it for electric potential energy and so on. So first of all, we have our work for gravity, and recall that work is really just equal to a force dot product with some sort of a displacement. And in the case of gravity, the force being exerted is m times g, and the distance is typically the height. And that's, it's important to remember that this is going to be the distance parallel to the force. I can rewrite this a little bit more specifically as the mass times the gravitational field strength times the displacement. And once again, being clear that this dot product indicates that they have to be in the same direction, or it only takes how much they're in the same direction. And one of the important things here is that I can kind of clarify this a little bit. This m is the property of a particle or a body, whatever, an object, property of a particle responsive to gravity. So this is really the term here, the idea here about a property or about a particle that tells us how responsive it's going to be to the gravitational field. G is nothing other than the gravitational field strength. Okay, now we've talked about G as the gravitational acceleration. Turns out that they're the same thing. And that's one of the more interesting things about gravity, is that its property that determines responsiveness to gravity happens to also be the property that determines resistance to change in motion. The same is not going to be the case with electrical charge, because obviously mass is still the property that's resistant to changes in motion. So it becomes, in some ways, it's actually clear what's going on, the differences between the different things when we're dealing with electricity than when we're dealing with gravity. And r is distance parallel. Typically what we want is distance parallel to g. That's really what we're interested in normally. But any distance will work, and we'll just find out what is actually parallel to it. So the other thing to bear in mind is that the work done by gravity is going to be equal to the opposite of the change in the gravitational potential energy. I'm going to give you a quick example here. Let's say that you have a potential energy initially of 20 joules, and then gravity does 5 joules of work. Well, really what this 20 joules is representing here, this potential energy, is this is potential to do work. And so if gravity then does 5 joules of work, that means that the gravitational potential energy has changed by 5. And I can write this a little bit better. Okay, so it's changed by 5, which means that the new gravitational potential energy will be 15 joules. So we initially had 20 joules of work that could be done by gravity. We actually did 5 of those joules, or gravity actually did 5 of those joules of work. And so we're left with just 15 joules of potential energy left. Now let's look at the picture that I have over here. So here is 0 meters. This is our starting point. And we're going to go 10 meters in the field of about 10 newtons per kilogram. Typically we've used G as 9.8, but just for the ease of calculations, we'll leave it at 10 for now. So that's 10 newtons per kilogram. That's really the same as 10 meters per second squared, but we're more interested in this unit structure at this point in time. And I've drawn the field vectors, so it's the same, it's a uniform field, so it's just going to be 10 in each case, and it's from our starting point to our end point, and it's through a distance of 10 meters. So one of the nice things here is that our G and our R are already lined up with each other. So all we need to do to find out the work done by gravity is just do mg times r. No need to worry too much about vectors. And let's just say that we start off with a mass of 2 kilograms. So then we have 2 times 10 times 10 gives us 200 joules of work was done by gravity. This equates to a change in the potential energy of negative 200 joules. And that also leads us to understand, hopefully, that the initial amount of potential energy was 200 joules. And that's suggesting that right here we have 0 joules of potential energy. Obviously, the actual starting and end amounts of potential energy are arbitrary. The key is that we have this change. This is the thing that I should put stars around. Okay, this is the thing that really matters. Because I could say that initially, you know what? Actually, initially we had 8,000 joules of potential energy. And then we wind up with 7,800 joules. We still had the change of negative 200 joules. So just to reiterate, when I'm doing the gravitational field, when I'm trying to incorporate gravitational field into work and into gravitational potential energy, all I need to do is mg times r, and that's going to be the amount of work done by gravity, or the opposite of the change in the gravitational potential energy, where gravitational potential energy should be interpreted as the potential to do work, the potential of gravity to do work. I've drawn my nice little field vectors. I've drawn my displacement vector. They happen to line up in this case, and then I just do my multiplication. This, once again, represents this gravitational field strength is the force that's exerted per kilogram in the case of gravitational potential. So if I were to change this mass from 2 kilograms to 4 kilograms, that gravitational field doesn't change. But obviously then the force would double, and the work done by gravity would then double in moving it through a certain distance. And that's really the beauty of using field strength, because it doesn't care what this is. It's kind of something that you tack on at the end to figure out exactly what's going on. So in the next video, what we're going to do is we're going to do a similar formulation for electric potential energy. The difficulty that we'll encounter there is that we don't have just one type of charge. We only have one type of mass. We do have 2 types of charge, and that makes things a little bit more interesting.